What if your reality was just a fraction of the whole picture? Welcome to the intriguing world of quantum mechanics. This enthralling journey begins at the dawn of the 20th century, a pivotal era that saw the birth of a radical new field in science, quantum mechanics. The classical Newtonian view of the universe, which had held sway for centuries, was about to be shattered. The architects of this revolution were pioneering physicists such as Max Planck, Albert Einstein, and Niels Bohr. Each of these luminaries made groundbreaking discoveries that forever altered our understanding of the universe. First, let's meet Max Planck. This brilliant mind proposed a revolutionary concept, that energy is not continuous but rather quantized. In other words, energy comes in distinct, indivisible packets, which he termed quanta. This was a major departure from the established norms of physics at the time. Next, we have Albert Einstein. While many know him for his famous equation, E equals mc squared, he also made significant contributions to quantum mechanics. Einstein explained the photoelectric effect, a phenomenon where light striking a material can eject electrons from it. This effect, he proposed, could only be explained if light itself was made up of particles or quanta of energy, which he called photons. Finally, we have Niels Bohr, who introduced the concept of quantum leaps. He proposed that electrons in an atom do not move in continuous orbits, as was previously thought, but rather they jump between fixed energy levels, or quantum states. These revolutionary ideas, as strange as they seemed, challenged the status quo and turned the world of physics upside down. But they were just the beginning. The stage was now set for even more bizarre discoveries in the realm of the very small, where the normal rules of physics ceased to apply. Quantum mechanics was born, paving the way for a new era in physics. A world of wave-particle duality, quantum entanglement, and superposition was waiting to be explored. These revolutionary ideas, as strange as they seemed, paved the way for a new era in physics, setting the stage for even more bizarre discoveries. Imagine a particle that can be in two places at once. Welcome to the double-slit experiment. This experiment is a cornerstone of quantum mechanics, showcasing the mind-boggling concept of wave-particle duality. Let's paint a picture. Picture a light source that emits particles, say photons or electrons, towards a barrier with two slits. Now, if the particles behaved like bullets, we'd expect them to pass through one slit or the other, hitting the screen behind in two distinct areas. But that's not what happens. Instead, we observe an interference pattern on the screen, as if the particles have passed through both slits simultaneously, interfering with themselves, creating a pattern of light and dark fringes. This is characteristic of wave behavior, not particles. Yet it gets even stranger. If we try to observe which slit the particle passes through, the interference pattern vanishes, and we see two distinct areas of impact, as if the particle has now chosen one path over the other. This suggests that the very act of observation changes the outcome. So what does this mean? It tells us that particles can exhibit both wave-like and particle-like properties, a phenomenon known as wave-particle duality. It suggests that the nature of reality may depend on our observation of it. This experiment challenges our classical understanding of reality, pushing us deeper into the quantum realm. What if two particles, no matter how far apart, could instantaneously affect each other? Enter the realm of quantum entanglement. Imagine two particles that are so deeply interconnected, they could be light years apart. Yet, if one changes, the other responds instantaneously. This isn't a science fiction tale, but a genuinely mind-boggling aspect of quantum mechanics known as quantum entanglement. Quantum entanglement defies our everyday intuition about the world. It's like having a pair of dice that, no matter how far apart they are thrown, always land on matching numbers. In the quantum world, these dice are tiny particles, like electrons or photons, that become entangled under specific conditions. Experimental confirmation of quantum entanglement came in the late 20th century through a series of groundbreaking experiments. These tests, known as Bell's theorem experiments, verified that entangled particles do indeed behave in this extraordinary way, shattering our conventional understanding of space and time. But quantum entanglement isn't just a curious phenomenon of the quantum world. It holds enormous potential for practical applications, particularly in the emerging fields of quantum computing and quantum communication. Quantum entanglement could enable the creation of ultra-secure communication networks and exponentially more powerful computers. Quantum entanglement, as strange as it seems, could be the key to future technologies. Can a cat be both alive and dead at the same time? Meet Schrödinger's cat. In the strange world of quantum physics, the answer isn't as straightforward as you might think. This paradox is at the heart of a thought experiment proposed by Erwin Schrödinger in 1935. A cat is placed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, breaking the vial and killing the cat. But until we open the box, we don't know whether the atom has decayed. According to quantum mechanics, the cat is in a superposition of states, both alive and dead, until we open the box. This thought experiment highlights the concept of quantum superposition, the idea that a quantum particle can exist in multiple states simultaneously until observed. This is not just about cats and boxes, but about the fundamental nature of reality. It's counterintuitive, to say the least, and it challenges our everyday experiences. But why does the act of observation change things? This is where the philosophical implications come in. Some argue that the observer is an active participant in shaping reality, while others suggest that there are multiple realities, one for each possible outcome. Quantum superposition challenges our everyday experiences and forces us to rethink the nature of existence. Can we ever know everything about a particle? Not according to Heisenberg's uncertainty principle. Journey into the world of Werner Heisenberg, a pivotal figure in quantum physics, who proposed an intriguing concept that continues to baffle even the sharpest minds today. The uncertainty principle, as it's known, states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It's like trying to watch a movie and read the book it's based on at the same time. You just can't do both perfectly. This principle isn't about the limitations of our measurement tools or our methods. Instead, it's a fundamental feature of the quantum world itself, an inherent fuzziness woven into the very fabric of reality. It's as though the universe, at its most basic level, refuses to reveal all its secrets at once. Not just a philosophical musing, the uncertainty principle has concrete implications. It's the reason why electrons don't spiral into the nucleus in atoms, and why we can't predict the exact moment a radioactive atom will decay. It reminds us that at the quantum level, our classical intuition breaks down and we enter a realm of probabilities and uncertainties. So if you ever find yourself yearning for absolute certainty, remember this. In the quantum realm, uncertainty is not just a limit to our knowledge, but a fundamental feature of reality.